Well, to once again state the obvious, like I always seem to at the beginning of these recordings, this is section 12. The first topic in here, end of section 11, we started talking about things related to temperature. And section 12 continues with that. The first topic being how the size of things changes with temperature. This has to be taken into account in quite a few different situations. Bridges, for example, have expansion joints in them because the bridge is going to get larger and smaller as the temperature changes with the weather. When you're casting metal, okay, like if you're gonna pour some liquid metal into a mold, which is the way they make a lot of different things, everything from engine blocks to, well, a lot of stuff. When the metal first hardens and becomes a solid, it's very hot. And it's going to contract as it cools off. And if you don't take this into account when you design the shape of the thing, when you make the mold, bad things can happen. It can crack or, get voids inside of it or something like that. And so anyhow, in many situations, all you care about is the change in something's length. If you're designing a bridge, especially a large bridge like those you would see over the Niagara River up by Grand Island, for example, nobody cares that the roadway gets slightly wider and slightly thicker in the summertime compared to the winter. The thing you're worried about is the length expanding and contracting. So what this could be actually is the metal rod that you'll be using in the next lab. Okay, lab number 12 actually has, I think it's 3 different parts, one of which deals with thermal expansion. And what you'll be measuring is a metal rod that actually looks a lot like this one. This one's aluminum. 3 of the setups have aluminum rods exactly like this one. And the other 3 setups have steel rods, which are the same length, but rustier because steel does that. Anyhow, what you do in the lab is that rod I just showed you is inside of a pipe, and you blow steam through the pipe. So the temperature of the rod increases from room temperature, where it started out, up to approximately 100 degrees Celsius, which is the temperature of the steam. And the change in temperature makes it get longer, okay? So the original temperature, T0, could be room temperature. And then this final temperature, T without a subscript, that could be 100 degrees if this is the experiment we're talking about here. Incidentally, the reason that things tend to get bigger as they get hotter is because, well, if you go back to what temperature means in the first place, it's the average kinetic energy per molecule. And I already talked about that in section 11 in the case of a gas, where the molecules just move around independently at random. And the higher the temperature, the faster they shoot around. In the case of a solid, it's a vibrational type of motion. Each molecule has an assigned position in the solid instead of being free to move around like in a gas or even a liquid. But it doesn't just sit at that assigned position. It behaves as if it's connected to it by a tiny little spring, and it vibrates back and forth. The higher the temperature, the more vigorously it vibrates. If the temperature gets too high, the crystal lattice basically shakes apart, and that's what we call melting it. So when things move around more vigorously, the space between them tends to increase, okay? If you had a room the size of this one, except it didn't have the furniture in it, you could probably get 200 or 300 people in here if the fire marshal didn't find out about it. But that would be if they were just going to crowd in and, like people on a subway at rush hour and just stand there mushed together. If they're going to dance, you wouldn't be able to get nearly that many people in here because with them moving around like that, everybody needs more space, okay? When the molecules are moving faster, they hit each other harder when they collide, and that tends to push them away from each other. So the general tendency for almost all materials is to get bigger when they get hotter. There are a few exceptions where some other effect overwhelms the usual tendency. Shrink wrap, for example, gets smaller when you heat it up. That's why it's shrink wrap. But for 99.999% of materials, that's what typically happens. Well, maybe it's not that many nines, but anyhow, L0 is the original length at T0, L final at the temperature T final. So this rod or wire or bridge or whatever this thing is has increased in length by an amount delta L. What does delta L depend on? Well, first of all, it depends on how much is there to expand in the first place. If I had a piece of wire that was 2 inches long, and I told you that between the winter and the summer, it changed from 2 inches to 3 inches long, you quite rightly would not believe me. On the other hand, if I had a piece of wire that was a couple 100 feet long and told you that as the seasons changed, it got an inch longer, that actually would probably be an underestimate. So the expansion is a percentage kind of thing. You're going to get more inches or centimeters when there are more inches or centimeters there to expand. Over here we have the temperature change. If the temperature goes up by 20 degrees, it's going to change in length twice as much compared to having the temperature go up 10 degrees. And finally, there's a property of the material. You can't quite, I should probably raise this up now, but the Greek letter alpha there stands for what's called the coefficient of linear expansion, which is, oh, now that's too high, okay. Some materials are just simply more sensitive to having their temperature changed than others. I mentioned that when you do the experiment, half of the setups get an aluminum rod and the other half get a steel rod. And what you'll find if you compare your result to what happens at one of the other tables where they've got the other kind of rod, you're going to find that the aluminum rods expand roughly twice as much as the steel rods, okay, going from room temperature to 100 degrees. The steel rods get roughly 0.5 millimeter longer, and the aluminum rods get a little over a whole millimeter longer. And that's the same length rod, same temperature change. The only difference is the material. And that property of the material is what's represented by the Greek letter alpha there. The expansion coefficient for various materials have been experimentally measured, and a short collection of those is, as you probably guessed, on your formula sheet. This is the formula sheet, the reference handout, and you'll see. Now, I'm sure they told you in math class that you don't want to say 24 times 10 to the negative 6, that standard scientific notation is 2.4 times 10 to the negative 5th. But quite often you see this sort of thing done in tables, because for somebody who's just quickly scanning around for the biggest number or the smallest number, it's kind of good to have everything to the same power of 10. And so, you know, like 9 times 10 to the negative 6 or 150 times 10 to the negative 6, it stands out better that this is the highest one and this is the smallest one when they're all to the same power of 10, and that's the reason they do that. So anyhow, example, maybe 40 meters is the distance from one electric pole to the next. The electric company does use aluminum for their wires. Yes, inside people's houses, you're supposed to use copper. That's the preferred material. But when you're the electric company and you're stringing wires for hundreds or thousands of miles, yeah, copper gets pretty expensive compared to aluminum. And aluminum is almost as good. It has a few problems that you don't want to use it for residential wiring, but it works fine up on the poles. And anyhow, so this wire is aluminum. One pole to the next is 40 meters, we'll say. 35 degrees Celsius is not at all unusual for a warm summer day around here. Minus 20 degrees, that's not unusual for a cold winter night around here. That would be, roughly somewhere in the general vicinity of 0 degrees Fahrenheit. And I have definitely left the house in the morning to go to work on days when it was colder than that. So let's say that I wrote 40 here, but I actually mean 40.00000, ridiculous number of significant figures. If it's that long on the summer day, how long is it on the winter night? And here's where you pause and work on the problem. Get your exercise. And here's where I give you a hint if you need one. If you look up aluminum in that table that I just showed you and put that in here for alpha, together with the other numbers given in the question. Now, one thing that can go wrong is delta T, don't make a sign error. T final minus T in it. From there to there is a difference of 55 degrees, not a difference of 15 degrees. Occasionally people get caught by that. Once you know delta L, this doesn't tell you the answer to the question. This tells you the amount of change. The question asked, what is the final length? So once you know delta L, you have to subtract it off from this to get the total length of the wire after it contracted. Because it's cooling off, it's going to get shorter, not bigger. So it should be smaller than 40 meters, not bigger. So if you still need time to work on that, now that I've thrown you hints, pause it here. Now, here's the part where I write it out in glorious detail. By the way, yes, I know that's the same letter we used for angular acceleration, but it's a completely different context. So there isn't really much chance for confusing the two ideas. And you know, even when you're working with two alphabets, there's only so many letters to go around. And after a while, you have to start recycling them unless you want to get into like the Hebrew alphabet and Nordic runes and Chinese characters. And anyhow, filling in the numbers. L0. And actually, if you put L final in there, it wouldn't really make any difference because it's almost the same thing. Why aren't you focusing? Oh, okay. Apparently, I just needed to call it on it. From table, that table I waved around a minute ago, you look up alpha for aluminum, and that's where I got that number. I'll explain what that unit means in a moment, but delta T means T final minus T initial, just like delta anything else means final minus initial. In the end, the rod is at negative 20 degrees. Originally, it was at positive 35. So delta T technically is negative 55 degrees. Like delta anything, increases are positive, decreases are negative, okay? So that times that, oh, and the way the units work out. Delta T is in degrees. The unit on alpha is degrees to the -1 power. So degrees divided by degrees cancels out. And whatever unit is on L0, that's going to be the unit that you get on delta L also. Okay, so you get a unit of length from here. So the change in length comes out with a unit of length on it. So the change in length is negative, again, meaning a decrease, 0.0528 of a meter, or in more familiar terms, about 2 inches. I guess I called it L0, didn't I? No, I for initial, O for original, whatever is your favorite notation. I guess I ought to make it match what it says on the handout. The question didn't ask for delta L, it asked for L final. So fill in the other numbers. Delta L is negative 0.0528. L initial is 40. Add the 40 to both sides. And to a completely ridiculous number of significant figures that nobody would ever actually measure the length of a wire to. That's the answer. More realistically, it would be, probably call it roughly 5 centimeters, so 39.95 would probably be a little more realistic way of rounding it. Well, sometimes you don't care about the length of something. Sometimes it's volume that matters. For example, if you've got some gasoline in a storage tank, nobody ever talks about the length of a piece of gasoline. With liquids, you're interested in the volume. That behaves the same way, okay? Delta V, just like delta L, depends on the total amount that's there to expand. If you've got 200 gallons, it'll expand twice as much compared to 100 gallons. Again, the temperature change and a property of the material, represented here by the Greek letter beta, which is like a Greek B, just like alpha is a Greek A. For materials where both are tabulated, you're going to find that beta is almost exactly equal to 3 times alpha. Basically, what's going on is here we're talking about 3-dimensional expansion. Here we're talking about 1-dimensional expansion. Well, you get an alpha's worth of expansion in each of these 3 dimensions. And so beta equals 3 alpha. Why introduce another symbol when you could just write 3 alpha? Well, like I said, nobody ever talks about the length of a liquid. So here's that table in the formula sheet again. You have solids in the column for the linear expansion coefficient. You have liquids in the column for the volume coefficient of expansion. But if you ever found yourself needing to calculate how much the volume of a piece of aluminum changed, you would need to multiply this by 3 and stick it in there. And I could run through another example where it was a liquid expanding instead of something's length, but it would look so much like this one, I don't think it's worth the time. So we'll just go right along to the next thing. Which is where it says heat. Or it will once I get it to focus again. Just wave my hand and abracadabra, it's focused. In everyday casual usage, 2 people talking on a street corner, the words heat and temperature get used kind of interchangeably. But if you get into their precise definitions, they are not quite the same. Well, they're not the same thing at all. They're 2 related concepts, but you know, it's like Connecticut is not the same thing as Massachusetts. They're kind of similar compared to, say, Alaska, but I don't know if that's a good analogy or not. Anyhow, heat is defined like this: energy that flows from one object to another due to a difference in their temperatures. You got a hot stove and you put a cold frying pan on that stove, and what happens next is energy flows from the stove into the frying pan, the flow of energy being driven by the temperature difference. That energy that's transferred is called heat. You might notice that the word heat is only properly used in the context of heat flow. People talk about heat content, again, casual street corner usage. So, I mean, even I do that. So, you know, a big tank of water like that holds a lot of heat. But technically, you're supposed to call that internal energy. We'll get back to that in section 13. It's kind of the physics equivalent of saying ain't. I mean, people do it all the time, but technically it's not correct. Heat refers to heat flow, okay? Units to measure heat in. And I've only got the first one there. I better boost this up a little more. Well, starting at the bottom of the list, I just got done saying heat is a type of energy, and therefore it can be measured in the same unit we've been measuring any other kind of energy in, which is joules. And increasingly, that is the way it's done. But there is also a whole separate system of heat units that exist partly for historical reasons, and they've persisted because they're kind of convenient. You see, heat at one time, if you go back a couple of hundred years, the connection between heat and mechanical work was not then known. Heat was thought of as being some kind of a fluid that flowed from high temperature things into low temperature things, the way water would flow from a saturated sponge into a paper towel that you sat it on top of. Okay, they called this fluid caloric. And so for units to measure heat in, which, as I said, they're kind of convenient for certain purposes, and so they persist to the present day, although the newer editions of the textbooks have kind of switched over to measuring heat in joules, at least for physics books. I'm not quite sure the chemists are on board with that yet, but the SI unit for heat is called a calorie. A calorie, like it says right there in front of you, is the amount of heat needed to raise a gram of water by 1 degree Celsius. Now, anybody who's ever been on a diet, or anybody who's known somebody who's been on a diet, in other words, basically everybody in the entire country, has heard the word calorie. It's like, oh, you don't want to eat that. It's got 600 calories in it. Well, that calorie, see, the unfortunate thing here is there are two different units that have the exact same name, okay? Sometimes people try to distinguish the big calorie from the little calorie by spelling the big calorie with a big C and the little calorie with a little c. And, you know, that's really helpful if I'm sitting here talking about it. You know, how do you tell if I just pronounced a capital C or a little c? Aside from that, people aren't even consistent about using a capital C when it's written down. But this larger calorie is the amount of heat needed to raise a kilogram of water by 1 degree Celsius. Now, physicists, of course, are much more sensible people than nutritionists. So we never call this a calorie. To us, it's a kilocalorie, and that eliminates the obvious potential for confusion about which one you're talking about. For purposes of this course, anyhow, a calorie is the little calorie, and the one based on a gram of water. And if I ever want to talk about the big calorie, I'll call it usually a kilocalorie. So actually, for our purposes, a Big Mac doesn't have 550 calories. It has 550,000 calories. And what you're doing is you're rating the energy content of the food. Okay, heat is a form of energy. When you eat something, your body basically burns it. It oxidizes the food just the same as a log in a campfire. It just, using some elaborate chemistry, does it at a lower temperature is all. In traditional British units, the corresponding unit for heat would be a British thermal unit, BTU for short. That is the amount of heat needed to raise a pound of water by 1 degree Fahrenheit. And, you know, it's just simply a matter of what's customary, that you rate the heat output of furnaces in BTUs and the energy content of food in calories, you could just as correctly talk about how many BTUs are in a Big Mac and how many calories per hour are put out by your furnace. And then back to where I started here, the mechanical equivalent of heat is the number of calories in a joule. Or if you're old school, it would be the number of BTUs in a foot-pound. The reason that there's a special name for something that's just a conversion factor between units, I mean, there's no special name for the number of centimeters in an inch. It's just the number of centimeters in an inch. But from a historical point of view, this was a big deal. As I mentioned earlier, it was not always known that there was a connection between mechanical work and heat, which kind of surprises me actually, because people have been starting fires by rubbing sticks together for thousands, probably hundreds of thousands of years. But actually it was James Prescott Joule, the guy that the unit is named after, that discovered that doing a certain amount of mechanical work on something always corresponded to adding a certain amount of heat to it. I had this illustrated to me very nicely when I was young and foolish, as opposed to now when I'm old and foolish. But it was before I'd ever even taken a physics course. I was just fooling around one day trying to make something in my dad's workshop. I don't remember anymore exactly what I was trying to do. I just very clearly remember that I had a piece of scrap metal, an old piece of metal rod in a vise, and I was cutting the end off it with a hacksaw. Now, no heat was added to that rod, okay? Look at the definition again. Energy that flows from one object to another due to a difference in their temperatures. Before I started, the saw was at room temperature and the rod was at room temperature. There was no hot object for heat to flow out of into this cold object, the metal rod. But when I went to take the rod out of the vise, okay, after the end fell off when I was done cutting, I grabbed the rod with my one hand and I started to loosen up the vise with my other hand. And then I let go of the end I'd been cutting there, and it was too late. I had a blister on my thumb for a week or two because that thing was flipping hot. Like I said, no heat flowed into that rod. Rather, what I did was work. Every stroke of the saw, force times distance, force times distance, force times distance. I was doing work against friction. Doing that work was equivalent to adding a certain amount of heat. In terms of what happened to my thumb, it was the same as if I'd cut the end off the torch or cut the end off the rod with an acetylene torch instead of a hacksaw. So, important point, a certain amount of mechanical work is equivalent to a certain amount of heat flow. You can make the molecules dance around faster inside of a piece of metal by doing work on them. You know, the molecules of the hacksaw were colliding with the molecules of the surrounding rod as the hacksaw passed through them and got them going faster that way. Or you can put it in contact with something that has faster moving molecules. And anyhow, that's what all the fuss is about here. The conversion between joules, and you can look this up. You can look up both of these things on the last page of your formula sheet, of course, where the table of units is. So, for a short example illustrating that, inspired by my own personal experience, Been a couple of times more recently that I've managed to burn myself on things that have had a lot of friction act on them also. You think I'd learn? So 100 joules of work will have the same effect on an object as 23.9 calories of heat. Or actually, you know, even like I said, heat can be measured in joules. You do the unit conversion the same way you would do any other unit conversion, converting revolutions into radians or watts into horsepower, any of those other things we've already looked at. So now for a little better look at the distinction between heat and temperature. Well, most of that's on the top of the next page. Just try and remember this. People usually call it specific heat for short, but the full name is specific heat capacity, which is why they use the letter C for it, I guess. It's a property of the material. Same page on the formula sheet. See, there's the expansion coefficients. There's the specific heat right underneath it for various materials. How much heat is needed to raise a gram of the substance by 1 degree Celsius? Okay, so turn the page. Yes, I do know how the document share function works in Zoom. But when I'm going back and forth between this thing and the blackboard all the time, it just seems easier to do it this way. So let's see, focus, there we are. We're going to use the letter Q for the amount of heat added to something. Measured in calories, which is kind of the way I lean, because I mean, I learned all this stuff 45 years ago, and that was pretty much the universal way of doing things back then. Or measured in it just seems to me, you know, as far, I mean, I can break old habits when there seems to be a good reason to, but it's so convenient to call the specific heat of water 1, rather, you know, 1 calorie per gram per degree, rather than if you measure things in joules, the specific heat is 4,186 joules per kilogram per degree. I don't know, I just like 1 better. I guess it doesn't matter as much with other materials, but whether you measure in calories or joules, Q is the amount of energy that you have added, the amount of energy added in the form of heat flow. T is the temperature. So delta T is how much does the temperature change and respond to having that heat added. So the distinction between heat and temperature. One factor that's in here is the specific heat. As I mentioned a moment ago, if you, and this follows directly from the definition of the calorie, if you add 1 calorie to 1 gram of water, the temperature goes up 1 degree. Now, if you add that same 1 calorie of heat to 1 gram of aluminum, the temperature goes up approximately 5 degrees. If you add 1 calorie to 1 gram of lead, the temperature goes up roughly 30 degrees. So same amount of heat, very different temperature changes, because some materials are more sensitive to having heat added than others. Okay, and that property of the material is the specific heat, like it says on the bottom of the previous page. So same heat, different temperature. There's the distinction between heat and temperature for you. The other factor is the mass. Let's say you had 2 pieces of the same material, steel. One is a paper clip, less than a gram. And the other one is a great big anvil like a blacksmith might have, probably 150 or 200 pounds of steel, something like that. Let's say you add the same amount of heat to both of them, okay? You strike a match, you hold the match in a pair of pliers so that you don't burn your fingers, letting it completely burn up. And let's say completely burning that match, maybe it gives off 1,000 calories, just to make up a number. It's probably more than that, but just for the sake of discussion. If you hold that burning match underneath the anvil until the match completely burns up, the temperature of the anvil will increase so little you would never notice the difference if you touch it. It'll be like a few hundredths of a degree, completely imperceptible to the touch. If you hold that same burning match underneath the paper clip until it completely burns up, if you were to then touch that paper clip, you don't want to touch that paper clip because you will have a paper clip shaped burn on your thumb. The temperature goes up a lot because temperature is the average kinetic energy per molecule. The anvil has a lot more molecules in it, so each one gets a much smaller share, okay? It's like if some crazy millionaire is standing on a street corner handing out $1 bills. It's one thing if he gives the whole $1 million to one person. It's another thing if he gives $1 to 1 million people. That has very little effect on any of those 1 million people. And, so it's how much money per person. And here it's how much energy per molecule. If you spread it across a much smaller number of molecules, it gives you a much greater temperature increase. So that's how the mass gets in there. Well, that's part of it anyhow. There's some other factors involved, but as you could see on that table of specific heat, denser things like lead tend to have smaller specific heats because a gram doesn't have as many molecules in it. Anyhow, there are other factors though, how the bonding works. Actually, am I looking at that backwards? Well, rather than dwell on that, I'm going to do a couple of examples, and then you're going to do, looks like just one, and then I'll talk about some other stuff. So we got 50 grams of steel, and it starts out at room temperature, and we're supposed to figure out how warm it is after that energy has been added to it. Looks like it's the right spot. 12B, I called this. Well, just to kind of get you warmed up, this one is just to drop numbers into the thing. You might want to try this one yourself before I run through it, because it's not the most challenging thing I'm going to go over today. But it says 100 calories of heat. Calories is Q, okay? The amount of energy. Q is the calories, or the equivalent number of joules if you prefer to measure things that way. M for mass. 50 grams. You go into that table I was waving around and look up the specific heat of, this was steel, was it? Yeah. Now, one question somebody might have is, wait a minute, he's been telling us over and over and over and over since the beginning of the course to convert grams to kilograms, but now he's leaving it in grams? Well, what I've really been telling you over and over since the beginning of the course is that your units have to be consistent with each other. And since the SI system is based on the kilogram, if it's going to be consistent with the other units around it, if you're sticking with SI units, you would need kilograms. In this particular case, though, if you look at the units up at the top of the column there in the table, we looked this up. This is measured in calories per gram per degree. If you've got grams here, you need grams there, so that grams divided by grams will cancel out. If you want to be all modern and SI-ish, go to the other column where the specific heat is measured in joules per kilogram per degree. If you go with that value, then you'd want kilograms here to match the kilograms there. But the real message, I guess, is keep an eye on the units so you don't get caught. Delta T means T final minus T initial. We know the original temperature. It started out at 20 degrees. The final temperature is what the question asked for. So got to solve it for T. So that's the setup. After this, it's just the math. 50 times 0.112 equals 5.6. And you know, there's different ways of working your way through the algebra that are all going to take you to the same place in the end. You could distribute the 5.6 across both terms for your next step. And I certainly wouldn't criticize you for that. But what I did that I thought seemed like it would get me to the answer a little quicker is I divided both sides by 5.6 to get it off of my variable. So 100 divided by 5.6 is 17.9. And then I added the 20 to both sides. That's how you do that one. Next question. Well, actually, before we get to the next question, it says something about conservation of energy. So I'll point it back at that and give you a few words of wisdom. So in this next question, you've got a hot thing and a cold thing that are placed in contact inside of a well-insulated container, okay? We're going to assume that no heat can get in or out of this container, that it's like it's surrounded with 5 feet of fiberglass insulation or something like that. So in that case, the heat lost by the hot thing has to equal the heat gained by the cold thing. Or you could generalize it, you know, if you could have 12 different things in the container, all with heat flowing between them, and it would still be true that the heat lost by the hot things has to equal the heat gained by the cold things, and it's conservation of energy. Heat is a type of energy, and so it can't just disappear and it can't just pop up out of nowhere. So in an insulated container or any kind of an isolated system, the heat gained by the hot stuff, or the heat gained by the cold stuff, equals the heat lost by the hot stuff. Well, losses are negative and gains are positive. So if you add the loss for the one thing to the gain for the other thing, saying it's the same amount of energy is going to mean that the total is zero. So the net heat flow from a system that has no heat flow in or out of it is zero. And that's the jumping off point for the next example and other examples like it. There's another part of our next lab that's kind of similar to this, except here, the idea is to predict the final temperature. The way the lab is set up, I thought maybe it might be a good idea to give you some idea of how all of these numbers got into the table in the first place. So you're given a piece of metal and you're supposed to determine its specific heat. It'll be the same kind of calculation that I'm about to go through here in this example, except when you do the lab, the specific heat of the piece of metal is the unknown you solve for. Whereas here, you treat the specific heats as something that somebody else has already measured earlier, and the final temperature is the unknown instead. So that's kind of the background information. Here's how you do it. So just to repeat myself, the jumping off point is that if you add up the Q's in a closed system, the total is zero. Q stands for the heat added to something. So if heat is in fact being lost, that term will be negative because the heat gained is equal to the heat lost. The total of the two is going to be zero because of conservation of energy. Each of those Q's that we're going to add up is equal to MC delta T. You are throwing a piece of hot metal into some cool water, very much like what you'll be doing in the lab. The heat gained by the lead plus the heat gained by the water adds up to zero because this term is actually negative. Fill in the numbers. We have 300 grams of lead. You go to the table, you look up lead's specific heat. A little more than 0.03. Delta T, well, just like I did before, T final minus T initial. Started out at 95 degrees. The temperature where it ends up is what we're looking for. And you see, that's how this term ends up being negative, because T final is lower than, the hot thing is going to cool off. So the final temperature is less than 95 degrees. And so a little number minus a big number, that's going to make this part of it negative, like I was saying. You have 100 grams of water. The specific heat of water in these units is 1. That follows directly from the definition of the calorie. The initial temperature of the water is 15 degrees. The water warms up as heat flows into it. So T final will be more than T initial, and that's what makes this term positive. What happens is heat flow is driven by a difference in temperature. So heat will flow until there no longer is a difference in temperature. And at that point, the system reaches what's called thermal equilibrium, which simply means that everything everywhere is at exactly the same temperature. At that point, heat no longer flows. Okay, so that's the setup. The physics is done at this point. The rest is the mathematical mopping up. Got to solve for T final. So if you want to see the intermediate steps, the step-by-step math, that times that is 9.15. $100 times 1. Hopefully nobody uses a calculator for that one. I have seen people during labs, grab their calculators to convert centimeters into meters. And it's like, just move the decimal. T final minus 15. Next, it would be a good idea to use the distributive property. 9.15 times T, 9.15 times 95. And 100 times T, 100 times 15. And then this probably sounds kind of familiar from some math class. What you want to do next is combine the like terms. Put the T terms together with the other T terms, put the constants together with the other constants. So 100T plus 9.15 T would be 109.15 T. Like that. I'm going to add these two negative numbers to both sides, okay? Add 869 to both sides, add 1500 to both sides. And when you put them together, that's 2369. Finally, you divide. So now it's your turn. Kind of a similar question, except this time I made the solid be the cold thing and the liquid be the hot thing. But, minor difference. So imitate the one that I just did and see if you can come up with that 37.8 for the answer. And while you think about that, I'm going to erase a place to do my work over here. Okay. I'm going to assume you have now given it your best shot. If you get stuck on these things, it's a video. You can back up and watch me do that again, find the part where I'm doing the part you got stuck on. But here come the details. 12-2. Just like the other one, the starting point is conservation of energy. Summation of the heats equals 0. The heat gained by the cold stuff equals the heat lost by the hot stuff. Each of those Q's is equal to MC delta T. So MC delta T for the mercury is equal to MC delta T for aluminum. Somewhere I can't remember if I found it myself in some used bookstore or if somebody else did and gave it to me, but I've got like a high school lab manual from about 1910 or something like that. And it's interesting how casual they are about mercury, I mean, you've got here kids that are like 12 or 15 years old, and it says right in the directions to stick your finger in the stuff. And, it's interesting how the attitude has changed over the years. Anyhow, fill in the numbers. We've got 200 grams of mercury. Its specific heat is not terribly different from, remember back over there, lead was 0.030, this is 0.33. They're both kind of similar heavy metals. T final minus T initial. Mercury starts out at 120 and cools down to T final. For the aluminum, you've got 90 grams of that, 0.217 for its specific heat. Final temperature for the aluminum is the same as the final temperature for the mercury, because, that's the final equilibrium temperature of the whole system. The heat flows until they reach the same temperature. And then the math. That times that, 6.6. that times that, 19.53. And then distribute. 6.6 times T, 6.6 times 120 equals 792. 19.53 T final, and then distribute the 19.53 across both terms. Combine the like terms. 6.6 plus 19.53 is 26.13. 792 plus 195.3, 973, and divide, and we're done. Well, that doesn't make any sense at all. Yeah, looks better like that. One disadvantage of standing here in an empty room doing this is when I do something stupid, there isn't somebody sitting over there that sticks up their hand and says, wait a minute, I don't understand why you did that. And then I can look at it and say, I don't understand why I did that either. Anyhow, I caught that one. If I do something stupid, send it in. I should probably tell everybody else the right way to do it. So everything in the container ends up at 37.8 degrees Celsius. The next thing it says, right underneath that example, is phase changes. I guess I'm not going to bother pointing it at the note packet, just so you can see two words. But to kind of introduce you to what's going on here, you see, everything I've done so far, what started out as a liquid ended up as a liquid. What started out as a solid ended up as a solid. There were no changes of state or changes of phase, whatever you want to call it. What if there are? Well, let's imagine, and actually it's an experiment that wouldn't be that hard to do, but it's even easier to just talk about it. So imagine you had a well-insulated container, and inside of that container, you put a sample of, it could be any crystalline solid. Could be, if you got it cold enough, it could be a chunk of oxygen, or it could be a chunk of aluminum, or basically anything. You see that there's crystalline solids and there's amorphous solids. Amorphous solids are things like glass and paraffin, and they behave a little bit differently. But well, I won't go off on a big tangent about that. Let's just say it's some ice, okay, as a typical example, although you're going to see the same behavior with a wide variety of other materials. And what you want to do is gather data for a graph of the temperature of your sample as a function of the amount of heat you've added, okay? In the container, along with our ice, or or whatever substance it is, there's a little electric heating element. And you can easily figure out how many watts of it's putting out from the voltage and the amps that are, you know, on your heating element there. So you're adding heat at a known steady rate. And the other thing that's in there with your sample, aside from the heating element, is a thermometer, so you can monitor the temperature. So you turn it on and you start collecting data. And what happens at first is you get pretty much a straight line, because Q equals MC delta T is a linear equation. Everything in the equation is to the first power, and that makes it a linear equation, and they call it a linear equation because when you graph it, you get a line. Now, actually, if you're working to a high level of precision, specific heats are somewhat of a function of temperature, okay? The specific heat of water when you go from 20 to 21 degrees is not precisely the same as the specific heat when you go from 30 to 31 degrees, for example. But, you know, unless you're trying to be a little more precise than we usually bother with in an introductory course, you can think of the specific. It's the same with expansion coefficients also. They can vary a little with temperature, but we don't worry about that in an introductory course like this. So to a pretty good approximation is a straight line. But then all of a sudden, without warning, you hit a plateau. If this is water that you're doing a sample, the experiment on, you have reached a temperature of 0 degrees Celsius. It's melting. Okay. What holds the water molecules together in a rigid structure is bonds between those water molecules. To make a solid into a liquid, where the structure is no longer rigid, you know, the molecules can flow around past each other, you have to break some of those bonds between molecules. Breaking those bonds requires energy. It's like pulling two Legos apart. You have to do work against friction to pull the Legos apart. And in a sort of a kind of a similar way, you have to supply energy to pull a couple of water molecules apart, okay? This does not increase their kinetic energy. You're increasing a type of potential energy that the molecules have relative to each other. The molecules in 0 degree liquid water are not moving any faster than the molecules in 0 degree solid water, ice in other words. So minute after minute goes by, more and more energy is being added. The temperature is, you know, assuming you're keeping everything well mixed, so your thermometer isn't like in a little hot pocket or something like that. The temperature does not change. This is probably the best illustration of all of the distinction between heat and temperature. Here you have a situation where you're adding heat with no resulting temperature change whatsoever. Well, finally, you get the ice completely melted. Once you're dealing with a liquid, the temperature starts to rise again, a little more steeply this time, because the specific heat of water is not the same thing as the specific heat of ice, liquid water. All of a sudden, you reach another plateau. If this is water we're talking about, the temperature is now 100 degrees. To make a liquid into a gas, you have to break all of the remaining bonds between molecules. And there again, you have to supply energy to pull, pull those molecules away from each other. Simply separating them does not make them go any faster. So 100 degree steam, the molecules have the same kinetic energy as in 100-degree water. That's what makes it 100 degrees, okay? But a lot of, actually, in the case of water, it's a lot of energy that's put in that you need to vaporize it, to boil it away. Once it's all completely vaporized, once it's all steam, the temperature starts to go up again, and that's where we will leave off with the story. Now, if you go on up to thousands of degrees, the gas will ionize. An ionized gas is thought of as a fourth state of matter, okay? A gas made up of neutral particles has significantly different properties from a gas made up of electrically charged particles. So a bunch of ions is called a plasma. And we're not going to take it that far. We're going to stop telling the story here. I always say a happy ending is a matter of knowing when to stop telling the story, because, you know, if you keep on going, eventually the princess has cancer and the prince can't remember who she is anymore. But you want to stop telling the story when they ride off, you know, in the coach after the wedding. And it's the same sort of thing here. We're going to stop telling the story at this point here, even though there is more to the story if you want to keep going. So that's what happens when you have a change of state. And by the way, if you start out with it hot and you come in the other direction, it's the same thing. If you start out with steam, you get to here, and a whole lot of energy comes out without the temperature dropping. All of that energy you put in to boil it, it comes back if you condense it back into water. This is why getting burned by steam is so much nastier than getting burned by water, okay? If you're cooking, and you know, what do college students live on? Macaroni and cheese dinners and ramen noodles. And both of these involve boiling water, okay? So if you throw the noodles in the boiling water and a drop of boiling water splashes out and lands on your hand, well, you know, that kind of hurts a little bit. But if you've got a lid on the pot and there's a good rolling boil in there and you lift the lid off to put the noodles in, if you lift the lid the wrong way so that steam blows out on your arm, it doesn't hurt a little bit. It hurts a lot. The reason is water has a very high heat of vaporization. I'll explain what that term means in just a moment here, but body temperature is somewhere around 30 degrees Celsius, roughly. So if 1 gram of boiling water lands on you, your flesh is going to absorb that much heat. If it's 1 gram of water going from 100 degrees down to 30 degrees, that'll be 70 calories. 1 gram of steam, in addition to that 70 calories there, this is about 540 calories, which means altogether that would be what, 610? 610 calories is going to burn you a heck of a lot worse than 70 calories, okay? So when it cools off, it comes back out. Okay, I guess it's time to point you with the clipboard again over here. It's also time to raise the clipboard up. There we go. So as I just described in quite a bit of detail, adding heat does not change the temperature while melting or boiling. The energy goes into breaking bonds rather than making the molecules move faster. How much heat per gram, or per kilogram if you'd rather do it that way, how much heat per unit mass is needed to melt something is a property of the material. Melting a gram of this takes a different amount of heat than melting a gram of something else. That property of the material is called its heat of fusion, or the full name is the latent heat of fusion, which is why they use the letter L for it. But assuming you want to measure mass in grams, it's the heat per gram to melt the stuff. If you have 2 grams, that would obviously take twice as much heat as melting 1 gram. So the mass times the heat of fusion is the amount of heat needed to melt whatever you're talking about. Similarly, the heat of vaporization, represented again by the letter L, this time LV instead of LF, the heat of vaporization is the amount of heat per gram to boil something, to make it turn into a gas. Now, if you are in fact drawing heat out, if you've got a gas turning into a liquid, or if you have a liquid turning into a solid, like, you know, if water is freezing, for example, if heat is flowing out, you have to remember on either one of these, you have to remember to stick a minus sign on there. With the formula for the heat that flows due to a change of temperature, it's automatic that it's negative when heat is flowing out. As I pointed out earlier, if you subtract the temperatures in the proper order, you'll get a minus sign if heat is flowing out. With this formula here, for heat that flows due to a change of state, instead of the heat that flows due to a change of temperature, you have to remember your own minus sign. Okay, it's not going to be automatic. You have to stick the minus sign on there yourself, which obviously qualifies as a booby trap that's waiting to catch you when you work through a problem like some of these. So I'm going to do a couple of examples, and then you're going to do a couple that are kind of like, you know, number 3 is a little bit like this one, number 4 is a little bit like, I'm pointing at all these things you can't see because they're a little further down the page. But anyhow, the first thing I should do is run through this one. So you've got some steam which has been elevated somewhat above the boiling point, superheated steam, and you draw heat out of it until it reaches a temperature of 50 degrees. Well, it's very difficult to keep it in the form of a gas all the way down to 50 degrees, okay? It's once you cross that 100-degree mark, it's going to be a liquid once you're below 100 degrees. So this is going to undergo a change of state along the way, along with the change of temperature here. And we want to know how much heat it gives off. So that works like this. To get the total heat given off in this process, there are 3 different things you have to add together. Just sort of picture in your mind what's going on. kind of like if you were sitting there watching this happen, take things in chronological order. The first thing that happens is the 120-degree steam cools down to 100 degrees. It gives off a certain amount of energy as it does this. So the amount of heat to go from the amount of heat to go from 120 degrees to 100 degrees is this. The next thing that happens is the 100-degree steam turns into 100-degree water, liquid water, giving off some more in the process. That's definitely going to take more space than I've allowed myself here. And for those people who are cursively challenged, that says steam to liquid, okay? So it gives off some heat as it changes from 120 degrees steam into 100 degree steam. Next, it gives off some more heat as it changes from 100 degrees steam into 100 degree liquid. Finally, once it's all liquefied, the temperature starts to drop again, and it gives off more heat. As it cools from 100 degrees to 50 degrees. So first it does this, next it does this, finally it does that, add them all together. And that's the total amount of energy, thermal energy, released as this, what started out as steam, goes through this process. The heat that flows due to a change of temperature is equal to mc delta T. So mc delta T for the steam. The heat that flows due to a change of state is equal to the mass times, in this case, it would be the heat of vaporization, okay? When you cross the boiling point, that's the heat of vaporization. When you cross the freezing point, that's the heat of fusion. So as I said a couple of minutes ago, here is here is a booby trap waiting for you to fall into it. You have to remember a minus sign here because heat is lost. If you were boiling the water, if it was changing over from a liquid to a gas, then this would be a plus because heat would be going in. But you're changing it from a gas to a liquid, heat is coming out. You need a minus. Last term, once again, we have a temperature change. And the heat that flows due to a temperature change is mc delta T. This time for liquid water rather than for steam. Occasionally, people want to combine these two terms here. mc delta T, where delta T is the difference between 120 degrees and 50 degrees. The reason you can't do that is that the specific heat of liquid water is different from the specific heat of steam. So those can't be combined. Throw the numbers at it. 4 grams of steam. And the specific heat of steam is somewhere in that table of specific heats. Yeah, there it is right there. It's the last one on the bottom in the right-hand column. 0.47. T final minus T initial. The specific, or the heat of vaporization for water is also, I put it right at the bottom of the page there. If I can get it to focus. Well, anyhow, oh, there it goes. I was gonna say, you can take my word for it. Heat of vaporization of water, 539 calories per gram. This is the same page that I've been flashing at you all day here. Last term, the mass is still 4 grams. It's a liquid now rather than a gas, but that doesn't make it get any heavier or anything like that. Specific heat of liquid water is 1. And temperature change, it goes from 50 degrees. Well, it ends up at 50 degrees. It started out at 100 degrees. So as it goes from 120 degrees down to 100 degrees, the steam gives off, minus sign means it's giving it off, gives off 37.6 calories. As the 100-degree steam turns into 100-degree liquid, it gives off 2,156 calories. And then once it's liquefied, going from 100 down to 50 degrees, gives off 200 calories. This kind of reinforces what I was saying before about it being so nasty to be burned by steam. Most of the heat given off in this case is given off by the change of state, not by the change of temperature. You put that together with that, and the temperature change only gives off, it adds up to 200, a little under 238 calories. The change of temperature gives off 238. The change of state gives off almost 10 times that much heat. Add those 3 things together, and it's, well, what you've got is negative 2393.6. And people sometimes look at where I've got the answer written there on the handout, and they say, well, do I have to have it in kilocalories? There's nothing in the question that says what unit you have to express the answer in. You could give it to me in BTUs if you wanted to, as long as you had the right number of BTUs. But the reason I put it in kilocalories there was just so I could round it off to 3 significant figures, which is our usual standard of accuracy for purposes of this course. This is 5 significant figures. That seems like too much, given that these were all through, well, you know, by 4 grams, I actually meant 4.00. Now, if this was a test, I'd give you full credit for this. I've already said earlier in the course that as long as you're within 2% of the correct answer, I'm not going to take off for how you've rounded your numbers. But what looks a little better to me is to round it off to 3-digit accuracy. So calories to kilocalories, you move the decimal over 3 places. And then I can round these last couple of things away and get it down to 3 significant digits. Whereas if I leave it in calories, you know, I need to have something there to show where the decimal point goes. That can make things unclear. Next example. Another one that I'm going to show you for sort of for a pattern to imitate. And then I'll turn you loose on those last couple. Example E kind of builds off the one that I just went through. It recycles some of the same numbers, in fact. This is another one of those conservation of energy problems where you've got an insulated container and the heat lost by the hot stuff equals the heat gained by the cold stuff. And you're supposed to predict the final temperature. So just like, I forget what I called it, but just like the example I went through a little while ago, total heat is equal to 0. The heat lost by the hot stuff is negative. The heat gained by the cold stuff is positive. You add it all up, it has to equal 0 because of conservation of energy. So the heat lost by the hot stuff, well, in this case, the hot stuff is steam, which is going to condense along the way. And so just like the other one that I went through, I could probably get another couple inches of that on the screen without losing anything. But just like this other one that I went through a minute ago, it's going to be 3 things added together, okay? It's once again going to be the heat to go from 120 down to 100, plus the heat to liquefy, plus the last thing in this other one said the heat to go from 100 down to 50 degrees. The thing that's different this time is we don't know the final temperature. Finding the final temperature is the point of the question. That's what it asks for. So instead of 100 to 50, it'll be 100 to T final. And aside from that, it's just a rerun of what I had there in the previous example. So heat to go from 120 degrees, 100 plus the heat to go from steam to a liquid, plus the heat (120 degrees to 100 degrees), steam to liquid, 100 degrees to T final. Just like before, except for the T final where the 50 degrees used to be. That's the heat lost by the hot stuff. The heat gained by the cold stuff, which is water in this. There is a part of the next lab that's similar to this also. You've got steam blowing out of a hose and you stick it in a cup of water, and as the steam bubbles through the water, the steam bubbles collapse almost immediately and it heats up the water. And you're going to use it as a way of measuring the heat of vaporization. Here it's a similar calculation. Well, it's not that similar, but there's some common elements, let's say. The heat gained by the cold stuff, well, what I mean by the cold water is the water that's been water all along, as opposed to the water that used to be steam, okay? This water starts out a liquid, it ends up a liquid, there's no change of state involved. So the heat that it absorbs is just equal to MC delta T. There's just one term. That's a little simpler than the other thing. So these first two things here, to go from 120 to 100 and also to liquefy, that is just a complete repeat of what happened over here. It's going to be these same two numbers again. So I'm not going to bother writing them out in as much detail. That is negative 37.6. That is negative 21.56. And I'm getting those numbers from example D over here. Okay, so they're still right there. Just recycled numbers. For the heat to go from 100 degrees to T final, MC delta T, 4 grams of steam. People get caught here. They stick the specific heat of steam in there. You would use the specific heat of steam. Well, I guess you can still see it over here. The specific heat of steam is for when you're above 100 degrees. Once it's below 100 degrees, I don't care that it used to be steam, it's liquid now, and it's the specific heat of liquid water that belongs in there. Delta T, T final minus T initial. When it first, well, you know, if you're going from 100 degrees down to T final, T initial would be that 100. So all of that added together is the heat lost by the hot stuff, the heat gained by the cold stuff. We've got 70 grams. Specific heat of water is 1. This water started out at 20 degrees and warms up to T final, the same T final that the steam cools down to, or the stuff that started out being steam anyhow. Okay. Recopy these two numbers. Over here, 4 times 1 is 4, and then you distribute it. 4 times T, 4 times 100. So 4T minus 400. 70 times 1 is 70. Distribute that. 70 times T, 70 times 20. Combine the like terms. 70T plus 4T is 74T. I added all these negative numbers to both sides and then put them all together, and that comes out 3993.6. That's 37.6 plus 2156 plus 400 plus 1400. Those four numbers added together give you this. Okay, what I have waiting for you over here is the main difference between these two and the ones that I just wrote out for you is that in the ones I just did, you've got steam that's cooling off. Here you've got ice that's warming up. Okay, so you'll have some places where it's a gain instead of a loss. A few other details are different, but just like before, the second one builds off of the first one. You'll be able to save yourself a minute or two by recycling some numbers. And yeah, this would be a place to pause it and see if you can do number 3, and then I'll go over it. And if you're back from having paused it, let's see if there's any helpful comments I can make before I just write out the whole thing. One thing that catches people sometimes is they get confused about when to use the heat of fusion and when to use the heat of vaporization. The heat of vaporization, vaporize means to become a gas. You use the heat of vaporization when you cross the boiling point. Here, you're crossing the freezing point. So you should have used the heat of fusion. There's usually some people who've used the heat of vaporization. So if that's what happened to you, go back and fix it. And I'll wait here while you pause it again. Is there anything else? I think I probably better just go ahead and write it all out. Let's see, I can probably recycle some of what I've got written here, actually. It's such a similar question. It's going to be number 3. And the total heat absorbed would be MC delta T to get from minus 30 degrees to 0 degrees. Okay, in other words, the heat absorbed while it's ice. And then when it reaches 0 degrees, what happens next is it melts. So instead of steam to liquid, it's going to be ice to liquid. Once it's liquefied, it goes from 0 degrees, I guess it says it ends up at 40. Yeah. So Q for a change of temperature, Q is equal to MC delta T. To melt ice, you add heat. So that's a plus sign now. And then MC delta T for the water after it melts. And then from there on down, I've got a completely different bunch of numbers, so I probably ought to just start fresh. Okay, we've got 50 grams of ice. You look in the table on the reference handout, and it gives the specific heat of ice as being 0.48 calories per gram per degree, or the equivalent number of joules per kilogram per degree, if you'd rather do it that way. T final minus T initial. Nice opportunity to make a sign error here. T final is, it warms up until it reaches 0 degrees. Original temperature, it started out at 30 below. It gives the heat of fusion as being 79.6 calories per gram. Still 50 grams for the mass. Specific heat of water is 1. T final minus T initial going from 0 to 40. Minus cancels, minus becomes a positive 30 times that, 720 calories. 50 times 79.6, 3,980 calories. And then 50 times 40, 2,000. 2,000 even. And then the last one, I'll point you at it again. The last one kind of modifies this into one of those heat lost equals heat gained kind of questions. So once again, 50 grams of ice, minus 30 Celsius, and to explain why the heat is flowing out of it, we're going to say that it's been placed in contact with 400 grams of aluminum. It starts out at 90 degrees, predict the final temperature. And I mean, you could figure out that all the ice ends up as liquid from the other information that's given there, but it makes it a little smoother if I just tell you that up front. So that's going to be kind of like this one was. Well, it's going to be kind of like that one was, but of course, you should pause the recording and try to do that yourself first and see if you can get the 22.7 degrees it says there. And now, probably you've tried it and hopefully you got it right and don't need to listen to me go through it, but just in case you really like the sound of my voice. Total heat equals 0. So just like before, the heat to get from -30 to 0 plus the heat for it to melt plus the heat to go from the melting point up to the final temperature. And then the hot stuff it's in contact with this time is aluminum. So like I said before, just kind of picture yourself watching this happen in front of you and write things down in chronological order. First, it warms up until it reaches the freezing point. Then it melts. And then it warms up from the freezing point up to the final temperature. And it absorbs heat in order to do each of those steps. And then the aluminum starts out a solid, it ends up still being a solid, so it's just MC delta T. Recycling the numbers from this other example over here. It's the same mass, it's the same temperatures. This first term is once again going to be 720 calories. And then it's the same amount of ice being melted. So that'll once again be 3980, just like it was before. Positive this time because heat is being added. And then we've got the MC delta T term to get from 0 degrees up to the final temperature. Okay. MC delta T for the melted ice to go from 0 to T final. For the aluminum, maybe I should get a little more space. MC delta T for the piece of aluminum that started out at 90 degrees and cools off to the same equilibrium temperature, but the water warms up to. And then there's the algebra. (400) times 0.217 equals 86.8. And you have to distribute that 86.8 across both terms. 86.8 times T, 86.8 times 90 equals 7812. Combine the like terms. 136.8 T final 3112. And you divide And that does it for section 12. The next page is the usual review for the upcoming exam. And then some people occasionally ask me, well, when do we get the last packet of notes? Turn the page. I didn't make a fourth packet of notes. I stuck the last 2 units of the course into the third packet of notes. So starting on page 41 in this same handout is section 13, and that will be the next video, which I might get time to record today, or I might not. We will see.